As you sit here watching this video, something terrifying is happening all around you. Something so vast, so silent, so unstoppable that no human being will ever be able to prevent it. The universe, this magnificent cosmos that we call home, is getting lonelier. Not in some poetic or metaphorical sense. No, in a very real, very measurable, very scientific sense. Every single second that ticks by on your clock, the universe loses contact with more of itself. Galaxies that existed within our reach are slipping away into the darkness, never to be seen again. Stars that once shone their light toward us are now moving so fast that their photons will never, ever arrive here. The cosmic web that connects everything together is stretching, thinning, dissolving. And the most haunting part of all this is that there is absolutely nothing anyone can do to stop it. Let me ask you something. Have you ever looked up at the night sky and felt a sense of connection? That feeling that you are part of something immense, something beautiful, something alive with stars and galaxies and nebulae? That feeling is based on a truth. Right now, we can see approximately 2 trillion galaxies from our position in space. 2 trillion. Each one containing hundreds of billions of stars. Each star potentially hosting planets. The universe right now looks full. It looks rich. It looks populated. But here is what nobody tells you. This view, this magnificent cosmic panorama that we enjoy today, is temporary. It is fading. And one day, far in the future, it will be gone completely. Imagine a civilization arising on a planet 50 trillion years from now. They develop telescopes. They look out into space. And what do they see? Nothing. Just their own galaxy, sitting alone in an infinite void of darkness. No other galaxies. No cosmic microwave background. No evidence that a Big Bang ever happened. They would look at their universe and conclude that they are alone, that their galaxy is all there is, that the cosmos is small and static and eternal. And they would be completely, utterly wrong. But they could never know it. Every piece of evidence that would tell them the truth has been erased by the expansion of space itself. That is the future of our universe. That is where we are headed. And the science behind this is not speculation. It is not theory. It is measured, confirmed, observed fact. Now, before we go any further, let me tell you what we are going to explore today. This video is going to take you on a journey from the very first discovery that told us the universe is expanding faster and faster, all the way to the final fate of every atom, every photon, every particle of matter in existence. We are going to explore the quantum mechanics behind this expansion. We are going to understand what dark energy actually is and why it is the most mysterious substance in all of physics. We are going to learn about cosmic horizons, the invisible boundaries beyond which information can never reach us. We are going to walk through the complete timeline of cosmic loneliness from now until the very end of time itself. And we are going to ask the hardest question of all. Can anything, any technology, any intelligence, any force in nature ever reverse this process? Everything I tell you today is based on published, peer-reviewed research, real observations, real mathematics, real physics. No speculation beyond what the equations allow. No bias. No agenda. Just the raw, beautiful, terrifying truth about the cosmos we inhabit. If this kind of deep cosmic exploration excites you, if you love understanding the universe at its most fundamental level, then do me a favor right now. Hit that like button, subscribe to this channel, and drop a comment telling me what you think about a universe destined for eternal isolation. Does it frighten you? Does it inspire you? Or does it make you appreciate this brief moment in cosmic history when we can still see the stars? Now let me take you back to the year 1998, because that is when everything changed. That is when two teams of scientists, working independently, racing against each other, made a discovery so shocking that it took over a decade for the world to fully appreciate what it meant. The story begins with a simple question. We knew the universe was expanding. Edwin Hubble had shown that back in 1929. Every galaxy is moving away from every other galaxy. Space itself is stretching. But the question in the 1990s was not whether the universe is expanding. The question was, how fast is it slowing down? Because everyone assumed it must be slowing down. Think about it. The universe is full of matter. Matter has gravity. Gravity pulls things together. So logically, the mutual gravitational attraction of all the matter in the universe should be acting like a brake, gradually slowing the expansion down. The only question was, how fast was this deceleration happening? Was the universe going to slow down and eventually collapse back in on itself in a big crunch? Or was it going to slow down but never quite stop, expanding forever but at an ever-decreasing rate? Two teams set out to answer this question. The Supernova Cosmology project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, led by Brian Schmidt at the Australian National University, with Adam Rees playing a crucial role in the data analysis. Both teams used the same method. They looked for a specific type of stellar explosion called a Type 1a supernova. These explosions are special because they all have roughly the same intrinsic brightness. They are what astronomers call standard candles. If you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate how far away it is. Simple inverse square law. So both teams found dozens of these distant supernovae in faraway galaxies. They measured their apparent brightness, they calculated their distances, and then they compared those distances to how fast those galaxies are moving away from us, which you can measure from the redshift of their light. If the universe were decelerating, these distant supernovae should appear slightly brighter than you would expect, because the galaxies would not have moved quite as far as a constant expansion rate would predict. Gravity should have held them back a little. But that is not what the data showed. The supernovae were dimmer than expected. Not brighter. Dimmer, which meant the galaxies were farther away than predicted. Which meant the universe had not been slowing down at all. It had been speeding up. The expansion of the universe was accelerating. When Adam Rees first saw the results, he thought he had made an error. He went back and checked his calculations multiple times. He looked for systematic problems in the data. He considered whether dust between us and the supernovae could be making them appear dimmer. He tested every possible alternative explanation. And one by one, every alternative fell away. The data was clear. The universe is accelerating. Brian Schmidt later described his reaction. He said his feeling was somewhere between amazement and horror. Amazement because it was one of the most profound discoveries in the history of cosmology. Horror because of what it implied about the future. An accelerating universe means something is actively pushing space apart. Something is working against gravity. Something is winning against the combined gravitational pull of all the matter in the entire universe. And whatever this something is, it is getting stronger relative to gravity with every passing moment, because as the universe expands, matter gets more diluted, gravity gets weaker, but this mysterious repulsive force remains constant or even grows. They called it dark energy, not because they understood it, but because they needed a name for something they could measure but could not explain. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics for their discovery. The Nobel Committee called it the most astounding discovery in cosmology in decades. And they were right. Because what this discovery told us is that the universe is not just expanding, it is running away from itself. And it is doing so faster and faster and faster, with no end in sight. This is where our story of cosmic loneliness begins. Because if everything is getting farther from everything else, and the rate at which things are separating is increasing, then eventually everything will be so far from everything else that no signal, no light, no information of any kind can ever bridge the gap. The universe will become a collection of isolated islands, each one alone in an infinite ocean of empty space, with no way to know that anything else exists. Now let us build this understanding properly, from the ground up. To truly appreciate why the universe is getting lonelier, we need to understand what expansion actually means. Because it is not what most people think. When we say the universe is expanding, we do not mean that galaxies are flying through space like shrapnel from an explosion. That is a common misconception. What is actually happening is far stranger and far more profound. Space itself is stretching. The fabric of the cosmos, the stage on which everything exists, is growing. Imagine an infinite sheet of rubber being pulled in all directions at once. Any two dots drawn on that sheet will move apart from each other, not because the dots are moving across the rubber, but because there is more rubber appearing between them. This is what Einstein's general theory of relativity predicts. Space is not a fixed, unchanging background. It is a dynamic entity. It can bend, it can warp, it can stretch, and it can grow. The equations of general relativity, specifically the Friedmann equations, derived by Alexander Friedmann in 1922, describe exactly how this stretching occurs. They tell us that the rate of expansion depends on what the universe contains. Matter slows expansion down through gravity. Radiation slows it down even faster, because radiation has both energy and pressure. But something with negative pressure, something that pushes outward instead of pulling inward, that would cause expansion to accelerate. For 70 years after Hubble's discovery, cosmologists assumed the universe contained only matter and radiation. They expected expansion to decelerate. They built their models around deceleration. The only debate was about how much deceleration. Then 1998 happened, and everything had to be rewritten. Now here is something crucial to understand. The expansion of space is happening everywhere, at every scale. But at small scales, other forces overpower it. Gravity holds galaxies together. Electromagnetic forces hold atoms together. The strong nuclear force holds atomic nuclei together. At these scales, expansion is irrelevant. It is utterly negligible. You are not getting bigger right now because of cosmic expansion. The Earth is not moving away from the Sun because of it. The Milky Way is not being torn apart by it. These structures are bound together by forces far stronger than the expansion rate at their scale. But at the largest scales, at distances of hundreds of millions of light years and beyond, no force is strong enough to counteract expansion. At those scales, galaxies are embedded in space, and space is carrying them apart. And the farther apart two objects are, the faster the space between them expands, because there is simply more space doing the stretching. This leads to something extraordinary. At sufficiently large distances, the expansion of space carries objects apart faster than the speed of light. I know that sounds impossible. Einstein said nothing can travel faster than light. But here is the subtlety. Einstein said nothing can travel through space faster than light. He said nothing about the expansion of space itself. Space can stretch at any rate it wants. There is no speed limit on the expansion of the fabric of reality. And when two objects are being carried apart by this expansion at a combined rate exceeding the speed of light, no information can ever pass between them. A photon emitted from one toward the other will never arrive, because the space between them is growing faster than the photon can cross it. This brings us to one of the most important concepts in this entire video. The concept of the cosmic event horizon. You are probably familiar with the event horizon of a black hole. It is the boundary around a black hole beyond which nothing can escape. Once you cross it, you are trapped forever. No signal you send can ever reach the outside universe again. Well, the accelerating expansion of the universe creates something analogous, but on a cosmic scale. There is a boundary around us, a sphere, beyond which the expansion of space is so fast that light emitted from objects beyond that boundary will never reach us. Ever, no matter how long we wait, no matter how patient we are. Those objects are causally disconnected from us. They exist, but for all practical purposes, they might as well not exist, because we can never observe them, communicate with them, or interact with them in any way. And here is the terrifying part. This cosmic event horizon is not static. Because the expansion is accelerating, this horizon is effectively becoming more restrictive over time. More and more objects that were once within our reach are crossing this boundary. Galaxies that we can currently observe, that we can currently point our telescopes at and study, will eventually be carried beyond this horizon by the expansion of space. And once they cross it, they are gone. Their light will be stretched to infinite wavelengths by the expansion, becoming completely undetectable. They will fade from view like a ship sailing beyond the horizon of an ocean, except this time, no ship will ever return. Let me give you a number to help you grasp the scale of this loss. Right now, the cosmic event horizon is roughly 16 billion light-years away from us. That means any galaxy currently within about 16 billion light-years can still, in principle, send us signals that will eventually arrive. But any galaxy currently beyond that distance is already lost to us forever. And because the universe is accelerating, this horizon is not expanding fast enough to keep up with the recession of distant galaxies. More galaxies cross it every moment. Roughly speaking, we are losing gravitational and causal contact with the equivalent of approximately 60,000 stars per second. 60,000 stars per second, vanishing beyond our event horizon, lost to us for all of eternity. Think about that. In the time it took me to say that sentence, hundreds of thousands of stars became permanently unreachable. Now let us go deeper into the physics of what is driving this acceleration. Let us talk about dark energy, because this is where quantum mechanics enters the picture in the most profound and mysterious way. Dark energy makes up approximately 68% of the total energy content of the universe. Not 68% of the matter, 68% of everything. The total energy budget of the cosmos. Matter, both the ordinary matter we are made of and the mysterious dark matter that holds galaxies together, accounts for only about 32%. So the dominant component of the universe, the thing that makes up more than 2/3 of everything that exists, is this mysterious, invisible, undetectable substance that we cannot see, cannot touch, cannot bottle, cannot measure directly, and do not understand. What we do know about dark energy comes from its effects. We know it has a constant energy density throughout space. As the universe expands and the volume of space increases, the total amount of dark energy increases proportionally. Unlike matter, which gets diluted as space grows, dark energy maintains the same energy per unit volume. This means that as the universe gets bigger, dark energy becomes more and more dominant compared to matter. Gravity, which is powered by the density of matter, gets weaker and weaker as matter dilutes. But dark energy stays the same. This is why the universe transitioned from deceleration to acceleration about 5 billion years ago. Before that point, matter was dense enough that its gravitational pull outweighed dark energy's repulsive push. After that point, dark energy won. and it has been winning ever since, more decisively with every passing moment. The simplest theoretical explanation for dark energy is something called the cosmological constant, often represented by the Greek letter lambda. This is a term that Einstein himself introduced into his equations of general relativity back in 1917. At the time, everyone believed the universe was static. It was not expanding or contracting. But Einstein realized that his equations naturally predicted a dynamic universe, one that would either expand or collapse. So he added this extra term, the cosmological constant, as a repulsive force to exactly balance gravity and keep the universe static. When Hubble discovered that the universe is actually expanding, Einstein called the cosmological constant his greatest blunder and removed it from his equations. But nature, it seems, had the last laugh, because in 1998, when the accelerating expansion was discovered, physicists realized that Einstein's so-called blunder was actually correct all along. The cosmological constant is real. There is a constant energy filling all of space, pushing everything apart. Einstein had the right idea for the wrong reason. Now here is where quantum mechanics comes in and creates what many physicists consider the biggest unsolved problem in all of theoretical physics. It is called the cosmological constant problem, and it is truly staggering in its magnitude. Quantum field theory, which is our best description of the subatomic world, tells us that empty space is not actually empty. This is one of the most counterintuitive results in all of physics, but it has been confirmed experimentally beyond any doubt. Even in a perfect vacuum, with no particles, no radiation, no anything, quantum fields are still fluctuating. Pairs of virtual particles constantly pop into existence and annihilate each other, borrowing energy from the vacuum for incredibly brief moments allowed by the Heisenberg uncertainty principle. These fluctuations give the vacuum a non-zero energy. The vacuum of space has energy. Empty space has a cost associated with it. This vacuum energy behaves exactly like a cosmological constant. It has constant energy density everywhere in space. It has negative pressure. It causes expansion to accelerate. In principle, this should be the explanation for dark energy. The vacuum energy predicted by quantum field theory should be the dark energy that we observe driving the universe apart. But there is a problem. A colossal, embarrassing, seemingly impossible problem. When we calculate the vacuum energy using quantum field theory, the number we get is approximately 10 to the power 120 times larger than the observed value of dark energy. Let me say that again so it really sinks in. The theoretical prediction is off by a factor of 10, followed by 120 zeros. This is not a 10% error. This is not a factor of 2 error. This is the largest discrepancy between theory and observation in the entire history of science. It is as if you asked someone how tall they are, and they said 10 to the power 120 meters instead of 2 meters. It makes no sense. The mathematics of quantum field theory is well tested. It gives incredibly accurate predictions for everything else we measure. Things like the magnetic moment of the electron, which quantum electrodynamics predicts to something like 12 decimal places of accuracy. And yet when we apply the same mathematics to calculate the vacuum energy, we get an answer that is utterly, absurdly, incomprehensibly wrong. This is the cosmological constant problem. And nobody, no physicist on Earth, has a convincing solution. Some have suggested that different contributions to vacuum energy from different quantum fields might cancel each other out almost perfectly, leaving just the tiny residual we observe. But this requires a cancellation so precise, so fine-tuned, that it is hard to see how it could happen naturally. Others have invoked the anthropic principle, suggesting that in a vast multiverse with many different values of the cosmological constant, we naturally find ourselves in a universe where the value is small enough to allow galaxies, stars, and life to form. But this explanation is deeply unsatisfying to many physicists because it does not actually explain anything mechanistically. The point is this: we know dark energy exists. We can measure its effects, we can describe it mathematically, but we do not understand its fundamental nature. Quantum mechanics tells us vacuum energy should exist, and it should drive expansion, and it does. But the numbers do not match. Something profound is missing from our understanding. Some piece of physics that we have not yet discovered must explain why the vacuum energy is so incredibly small compared to what we would naively calculate. Now, the cosmological constant is not the only possible explanation for dark energy. There are other theoretical candidates, and I want to tell you about them because they lead to very different futures for the universe and very different timelines for cosmic loneliness. The second candidate is called quintessence. Unlike the cosmological constant, which has a fixed energy density that never changes, quintessence is a dynamic field. Its energy density can evolve over time. It can be stronger at some epochs and weaker at others. Quintessence is inspired by the inflaton field, the hypothetical quantum field that drove the incredibly rapid expansion of the very early universe during the epoch of cosmic inflation. If one dynamic field drove exponential expansion in the past, perhaps a different dynamic field is driving accelerated expansion today. The key difference between quintessence and the cosmological constant is the equation of state parameter, which physicists call W. For the cosmological constant, W equals exactly -1. Always, everywhere, at all times. For quintessence, W can vary. It can be close to -1, but slightly different. And it can change over time. Why does this matter? Because if W is slightly less than -1, we enter the territory of what is called phantom energy. And phantom energy is terrifying. If dark energy is phantom energy, then its energy density does not just stay constant as the universe expands. It actually increases. The faster the universe expands, the stronger phantom energy gets, which makes the universe expand even faster, which makes phantom energy even stronger. It is a runaway process, a positive feedback loop, and it leads to a scenario called the Big Rip. In the Big Rip scenario, the expansion rate increases so rapidly that it eventually overcomes all forces, not just gravity at cosmic scales, but gravity at local scales too. First, galaxy clusters are torn apart. Then individual galaxies. Then star systems. Then planets. Then atoms. Then atomic nuclei. The very fabric of space-time is ripped to shreds in a finite amount of time. In this scenario, the universe does not slowly fade into loneliness over trillions of years. It is violently destroyed in a catastrophic finale. Current observations suggest that W is very close to -1, within about 5 to 10%. It is entirely consistent with being exactly -1, which would mean dark energy is simply the cosmological constant. But it could also be very slightly less than -1, which would eventually lead to a Big Rip. We do not yet have precise enough measurements to tell the difference with certainty. In fact, results from the Dark Energy Spectroscopic Instrument, known as DESI, released in 2024, showed tantalizing hints that dark energy might not be perfectly constant. Their data, which mapped the three-dimensional positions of millions of galaxies and quasars, suggested that the equation of state parameter might be evolving over time. Specifically, their results were consistent with dark energy being somewhat weaker in the past and somewhat stronger now. Or possibly the other way around, depending on which model you fit to the data. These results are not yet conclusive. The statistical significance is not overwhelming, but they represent the first real observational hint that dark energy might be more complicated than a simple cosmological constant. If dark energy is indeed evolving, this changes the timeline of cosmic loneliness, but not the ultimate outcome. Whether the universe ends in a slow heat death or a rapid big rip, either way, everything eventually ends up alone. Isolated, cut off from everything else. The specifics of the timing change, but the fundamental conclusion does not. Now let us talk about what this acceleration means for the structure of the observable universe and how our cosmic neighborhood is slowly dissolving. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It is a sphere centered on our location with a current radius of approximately 6.5 billion light-years. You might wonder how we can see things 6 billion light-years away if the universe is only 13.8 billion years old. The answer is expansion. Light from the most distant objects we can see started traveling toward us 13.8 billion years ago. But in the time that light was traveling, the space between us and its source was expanding. So by the time the light arrives, the source is much farther away than the distance the light actually traveled. The object that emitted the cosmic microwave background radiation, which is the oldest light we can see, is now 46 billion light-years away, even though its light traveled for only 13.8 billion years. But here is the critical distinction. There is a difference between the observable universe, the region we can currently see, and the accessible universe, the region we can ever hope to interact with in the future. Because of accelerating expansion, these are two different things, and the accessible universe is smaller than the observable one. The cosmic event horizon defines the boundary of the accessible universe. It tells us the farthest distance from which a photon emitted today can ever reach us. And because expansion is accelerating, this event horizon is more restrictive than the particle horizon that defines what we can currently see. There are objects in our observable universe right now, objects we can see and study today, whose light we will never receive again. If they were to send a signal right now, that signal would never arrive here. They are already beyond our event horizon. We can see their past, but we have no access to their future. Think about how strange this is. You can point a telescope at a galaxy and observe it as it was billions of years ago. But that galaxy, as it exists today, is already unreachable. It has crossed our event horizon. It is in our past light cone, but outside our future light cone. We can see its history, but can never influence or be influenced by its future. It is like reading the diary of someone who has already sailed beyond the edge of the world, knowing you will never hear from them again. And the situation only gets worse with time. As the universe continues to accelerate, more and more galaxies cross our event horizon. The accessible portion of the universe shrinks relative to the total universe, and the light from galaxies that have already crossed the horizon continues to arrive for a while, but it is increasingly redshifted, increasingly stretched by expansion, until eventually it becomes so feeble, so low in energy, that no conceivable detector could ever pick it up. The galaxy does not just become unreachable, it becomes invisible. It effectively ceases to exist, from our perspective. Let me paint you a picture of what this means over time. Right now, we can see about 2 trillion galaxies. Our local group, which contains the Milky Way, Andromeda, and about 80 smaller galaxies, is gravitationally bound. These galaxies will never be separated by expansion, because their mutual gravity is strong enough to overpower the expansion at their relatively small scale. But every other galaxy in the universe, every galaxy outside our local group, is ultimately doomed to disappear beyond our horizon. In about 100 billion years, the expansion will have redshifted the light from all external galaxies to such extreme wavelengths that they will become undetectable even with perfect instruments. the sky outside our local group will go dark. In about 1 to 2 trillion years, even the cosmic microwave background, that faint afterglow of the Big Bang that permeates all of space, will be redshifted to wavelengths longer than the observable universe itself. It will become undetectable. The last piece of evidence that a Big Bang ever occurred will have been erased. This is what I meant at the beginning of this video when I described a future civilization seeing nothing but their own galaxy. It is not that the rest of the universe will have been destroyed. It will still be out there. Trillions of galaxies, vast cosmic structures, all of it still existing. But none of it visible. None of it detectable. None of it accessible. To any observer confined to the local group, the entire universe will appear to be one single galaxy floating in an infinite, empty void. And this is not the result of some catastrophe or some exotic physics. This is simply what happens when you have accelerating expansion acting over long periods of time. This is the natural, inevitable, thermodynamically driven future of a universe containing dark energy. The loneliness is built into the laws of physics. Now, I want to take you even deeper. I want to show you how quantum mechanics is intimately connected to this story of cosmic expansion and cosmic loneliness. Because the connection between the quantum world and the expanding universe is far more profound than most people realize. Let us start at the very beginning. The large-scale structure of the universe. All those galaxies, galaxy clusters, cosmic filaments, and vast empty voids. Where did they come from? How did the universe go from a nearly perfect, smooth, uniform plasma in its earliest moments to the lumpy structured cosmos we see today? The answer is quantum mechanics. During the epoch of cosmic inflation, the very first fraction of a second after the Big Bang, the universe underwent exponential expansion. Space grew by a factor of at least 10 to the power 26 in a tiny fraction of a second. During this expansion, quantum fluctuations in the inflaton field, the field driving inflation, were stretched from subatomic scales to cosmic scales. These fluctuations are the result of the Heisenberg uncertainty principle. You cannot simultaneously know a field's value and its rate of change with perfect precision. There is always inherent quantum fuzziness. In normal circumstances, these fluctuations are incredibly tiny and average out, but inflation took them and stretched them to enormous sizes before they could average out. These stretched quantum fluctuations became the seeds of all structure in the universe. Regions where the quantum fluctuation was slightly positive ended up with slightly higher density. Regions where it was slightly negative ended up with slightly lower density. Over billions of years, gravity amplified these tiny differences. Higher density regions attracted more matter and grew denser. Lower density regions lost matter and became emptier. Eventually, the high density regions became galaxies and galaxy clusters, while the low density regions became the vast cosmic voids. So here is the profound connection. The very structures that make the universe interesting, the galaxies and stars and planets that provide homes for matter and potentially for life, were created by quantum fluctuations. Quantum mechanics built the universe's structure. And now, dark energy, which may itself be a quantum phenomenon, the vacuum energy of quantum fields, is tearing that structure apart. Quantum mechanics giveth, and quantum mechanics taketh away. There is another deep connection between quantum mechanics and the expanding universe that I want to tell you about. It involves one of the strangest phenomena in all of physics, a phenomenon that Einstein himself called spooky action at a distance. Quantum entanglement. When two particles are quantum entangled, their properties are correlated in a way that has no classical explanation. Measuring one particle instantaneously determines the state of the other, regardless of how far apart they are. This correlation does not allow faster than light communication, because you cannot control what outcome you get, but it is a real, verified, experimentally confirmed feature of quantum mechanics. Now, what happens to quantum entanglement in an expanding universe? This is an active area of research, and the results are fascinating. As space expands between two entangled particles, the entanglement is affected. The expansion introduces what physicists call decoherence. Decoherence is the process by which quantum correlations are degraded, turning a quantum system into something that behaves classically. In an accelerating universe, the cosmic event horizon acts somewhat like an observer for quantum systems. It introduces a form of environmental decoherence. Two particles that were once maximally entangled, if separated by the expansion of space to distances beyond the event horizon, lose their quantum correlation. The entanglement is not just hidden or inaccessible. According to some analyses, it is genuinely degraded. The universe's expansion is literally destroying quantum connections between distant systems. This is cosmic loneliness at the quantum level. Not just galaxies being separated, not just light being unable to travel between distant points, but the very quantum fabric of reality being torn. The fundamental correlations between particles, the spooky connections that Einstein wondered about, being severed by the relentless expansion of space. There is yet another quantum mechanical process that contributes to the loneliness of the universe, and this one is perhaps the most beautiful and the most tragic. It is called Hawking radiation, and it connects the physics of black holes to the ultimate fate of the cosmos. In 1974, Stephen Hawking made one of the most stunning theoretical predictions in the history of physics. He showed that black holes are not truly black. They emit radiation. Not because anything escapes from inside the black hole, which is impossible, but because of quantum effects at the event horizon. Near the event horizon of a black hole, quantum fluctuations in the vacuum constantly produce pairs of virtual particles. Normally, these pairs annihilate each other almost immediately, before anyone can notice them. But at the event horizon, something special happens. One particle of the pair can fall into the black hole, while the other escapes into space. The escaping particle carries away energy, which means the black hole loses energy, which means it loses mass. Very slowly, photon by photon, quantum fluctuation by quantum fluctuation, the black hole evaporates. For stellar mass black holes, this process is unimaginably slow. A black hole with the mass of our Sun would take approximately 10 to the power 67 years to evaporate. That is a 1 followed by 67 zeros. For supermassive black holes like the ones at the centers of galaxies, the time scale is even longer, around 10 to the power 100 years or more. But in a universe with infinite time ahead of it, even these colossal timescales are finite. Eventually, every black hole will evaporate. The last organized structures in the universe will dissolve into a faint mist of radiation. And here is the connection to cosmic expansion. In an accelerating universe approaching what physicists call de Sitter space, the cosmic event horizon itself behaves like a black hole turned inside out. It has a temperature. It emits radiation. This is called Gibbons-Hawking radiation. The radiation is incredibly faint, with a temperature of approximately 10 to the minus 30 Kelvin, far colder than anything we can currently measure. But it exists. The cosmic horizon glows, just barely, with the faintest possible thermal radiation. In the far future, when all stars have died, all matter has decayed, and all black holes have evaporated, this Gibbons-Hawking radiation from the cosmic horizon will be the only source of energy in the entire observable universe. And it is so feeble, so cold, so insufficient, that it cannot power any complex process. It cannot sustain any form of computation. It cannot support any form of life or intelligence, no matter how minimal. It is the final, dying whisper of a universe fading into eternal silence. Now let me take you to something that connects quantum mechanics to the loneliness story in yet another way. Something that speaks to the very stability of matter itself. I am talking about vacuum decay. The Higgs field, which was confirmed to exist with the discovery of the Higgs boson at CERN in 2012, permeates all of space. It gives mass to fundamental particles. Without it, electrons would be massless, atoms could not form, chemistry would not exist, and neither would we. The Higgs field has a certain value everywhere in space, and this value determines the laws of physics as we know them. But here is the disturbing possibility. The Higgs field might not be in its lowest possible energy state. It might be in what physicists call a metastable state, a local minimum rather than the true global minimum of its energy landscape. Think of it like a ball sitting in a small valley on the side of a mountain. The ball is stable in the sense that small pushes will not dislodge it. It will roll back to the center of the valley. But there is a deeper valley farther down the mountain, and if the ball ever gets enough energy to clear the ridge, it will roll down to the lower valley and never come back. If the Higgs field is metastable, then it is possible for a process called quantum tunneling to push it over the energy barrier and into the lower state. Quantum tunneling is a purely quantum mechanical phenomenon where particles or fields can pass through energy barriers that they classically should not be able to surmount. It happens because quantum mechanics deals in probabilities, not certainties, and there is always a non-zero probability of being on the other side of a barrier. If this tunneling event were to occur anywhere in the universe, a tiny bubble of space where the Higgs field has transitioned to the true vacuum would form. This bubble would expand at the speed of light, converting all the space it touches into the new vacuum state. Inside this bubble, the laws of physics would be different. The masses of particles would change. Atoms as we know them might not be able to exist. Chemistry would be impossible. Any structure, any planet, any life form touched by this bubble would be instantaneously destroyed, not by violence, but by having the rules of existence rewritten. Based on measurements of the Higgs boson mass and the top quark mass, our universe appears to be right on the edge between stability and metastability. The calculations suggest we are probably metastable, but only barely. If we are metastable, the expected lifetime before vacuum decay occurs is enormously long, much longer than the current age of the universe, possibly 10 to the power 100 years or more. So it is not something to worry about on human timescales. But it represents yet another quantum mechanical threat to the long-term existence of structure in the universe. Another way in which the cosmos might ultimately achieve perfect, final, irreversible loneliness. Not through the slow fading of expansion, but through the sudden rewriting of reality itself. Let me now take you through the full timeline of how the universe's loneliness evolves. I want you to understand the complete picture, from now all the way to the end of time, step by step, era by era. We currently live in what cosmologists call the stelliferous era, the age of stars. This is the epoch during which hydrogen gas collapses under gravity to form stars. Stars burn their nuclear fuel and shine, planets form around stars, and complex chemistry is possible. It is the age in which life can exist. It is the age in which we find ourselves. But the stelliferous era is not eternal. It is actually relatively brief in the grand timeline of the universe. Star formation requires cold, dense clouds of hydrogen gas. These clouds exist in abundance now, but they are being gradually consumed. Every star that forms uses up hydrogen. Some of that hydrogen is recycled when stars die and expel their outer layers. But not all of it. Some is permanently locked away in white dwarfs, neutron stars, and black holes. and some is ejected from galaxies entirely by supernova explosions and active galactic nuclei, where it disperses into intergalactic space and becomes too diffuse to ever form stars again. The rate of star formation in the universe peaked approximately 10 billion years ago, about 3 to 4 billion years after the Big Bang. Since then, it has been declining. We are already past the golden age of star birth. The Milky Way currently forms roughly 1 to 2 new stars per year. That sounds like a lot, but compared to the peak rate in the young universe, it is quite modest. And it will continue to decline. In about 4 to 5 billion years, the Andromeda Galaxy will collide and merge with the Milky Way. This event will actually trigger a temporary burst of new star formation as gas clouds are compressed by the collision. The merged galaxy, sometimes called Milkomeda or Milkdromeda, will be a large elliptical galaxy. But this burst of star formation will be brief. After the merger settles, star formation will resume its decline. Meanwhile, all the other galaxies in the universe, every galaxy outside our local group, will be receding ever faster. By the time the Milky Way and Andromeda merge, many currently visible galaxies will already be approaching our event horizon, within 100 billion years. The sky beyond our local galaxy will be effectively empty. The smallest, longest-lived stars in the universe are red dwarfs. These are stars much less massive than our Sun, burning their hydrogen fuel so slowly and so efficiently that they can shine for trillions of years. The smallest red dwarfs, about 8% the mass of the Sun, will burn for roughly 10 trillion years, nearly 1,000 times the current age of the universe. So stars will continue to exist for a very long time. But eventually, even the longest-lived red dwarfs will exhaust their fuel. Around 100 trillion years from now, approximately 10 to the power 14 years, the last star in the universe will flicker and die. Its nuclear furnace will run out of hydrogen. It will contract, cool, and fade into a white dwarf, then over trillions more years, cool further into a black dwarf, a cold, dark, dead stellar remnant. When the last star dies, the stelliferous era ends and the degenerate era begins. This is the age of remnants. The universe will be populated by dead objects. White dwarfs cooling toward absolute zero. Neutron stars spinning down and losing their magnetic fields. Brown dwarfs, objects that were never massive enough to ignite nuclear fusion in the first place, drifting cold and dark through space. And black holes, patient and long-lived, sitting at the centers of dead galaxies. In the degenerate era, the universe is already profoundly lonely. No stars shine. No light illuminates the cosmos except the fading glow of cooling remnants, growing dimmer by the eon. Occasionally, very rarely, two brown dwarfs in a galaxy might collide and merge, briefly igniting a new star that shines for a few billion years before exhausting its fuel. These events will be incredibly rare, perhaps one per galaxy per trillion years, or even less. Brief, isolated flickers of light in an ocean of darkness. Now, during the degenerate era, something else is happening at the quantum level. If grand unified theories of particle physics are correct, protons are not eternal. They decay. The half-life of the proton is predicted to be somewhere between 10 to the power 34 and 10 to the power 41 years, depending on which specific model you use. Experiments have not yet detected proton decay, which tells us the half-life must be at least 10 to the power 34 years. But that does not mean it does not happen. It might just take longer than we have been able to test so far. If protons do decay, then by roughly 10 to the power 40 years, all ordinary matter in the universe will have dissolved. Every atom, every molecule, every white dwarf, every neutron star, everything made of protons and neutrons will have decayed into lighter particles, positrons, electrons, neutrinos, and photons. These particles will disperse into space, adding to the ever-growing emptiness. After proton decay completes, the only macroscopic objects left will be black holes. Everything else will be a thin gas of fundamental particles and radiation spread across impossibly vast spaces, too diffuse to ever interact or form structures again. This brings us to the black hole era. From approximately 10 to the power 40 years to 10 to the power 100 years. Black holes dominate the cosmic landscape. They are the last bastions of organized matter and energy in the universe, the most complex objects remaining. But even they are not eternal. Hawking radiation ensures that every black hole, no matter how massive, will eventually evaporate. The rate of evaporation is inversely proportional to the square of the black hole's mass. Small black holes evaporate quickly. Large ones evaporate slowly. A black hole with 10 times the mass of the Sun will evaporate in approximately 10 to the power 67 years. A supermassive black hole with 1 billion solar masses will take approximately 10 to the power 99 years. The most massive black holes we know of might survive until 10 to the power 100 years or beyond. As a black hole evaporates, it slowly shrinks, growing hotter and radiating more intensely. In its final moments, it releases a burst of particles and radiation, then vanishes entirely. This final burst is the last hurrah of a structure that existed for unimaginable eons. The last gasp of complexity in a dying universe. When the last black hole evaporates, the universe enters its final state, the dark era. Beyond 10 to the power 100 years, there is nothing left but a sparse, ultra-thin gas of photons, neutrinos, electrons, and positrons, all at impossibly low temperatures, spread across distances so vast that individual particles may be separated by distances greater than the current observable universe. In the dark era, nothing happens. Nothing can happen. The universe has reached maximum entropy, the state of greatest disorder. There are no energy gradients to drive any process, no temperature differences to power any engine, no structures to collapse or decay, no chemistry, no complexity, no information processing of any kind. The second law of thermodynamics tells us that entropy always increases in isolated systems. The universe, being the ultimate isolated system, marches inexorably toward maximum entropy. And maximum entropy is the loneliest possible state. It is a state where everything is uniform, everything is in equilibrium, everything is the same everywhere. There are no patterns, no structures, no differences between one region of space and another. Just an infinite, featureless, homogeneous void with nothing to distinguish any point from any other point. A cosmos without content. Existence without meaning. This is what physicists call the heat death of the universe. Not because it is hot, but because all heat, all thermal energy, is uniformly distributed. There are no hot spots and cold spots. No sources and sinks. Just a uniform, inert, empty universe at a temperature asymptotically approaching absolute zero, but never quite reaching it. And this state, according to our best understanding of physics, is eternal. It never ends. The universe does not restart. It does not collapse. It does not bounce back. It just sits there, empty and cold and alone, for the rest of time, which is infinite. Let me pause here for a moment because I want to make sure you fully appreciate the scale of time we are talking about. The current age of the universe, 13.8 billion years, is absolutely nothing compared to what comes next. If you were to write the age of the universe as a number, it has 10 digits. The time until the last star dies has 14 digits. The time until the last black hole evaporates has 100 digits. And after that, the dark era stretches for eternity. The fraction of cosmic time during which the universe is interesting, during which things happen, during which structures exist, and light shines, and life is possible, is essentially zero. It rounds to nothing. We live in an infinitesimally brief flash of complexity, sandwiched between the Big Bang and an eternal dark emptiness. Part 2W. This is the ultimate loneliness. Not just spatial isolation, where everything is far from everything else, but temporal isolation. We live in a tiny bubble of time when the universe is rich and dynamic. Before this bubble, the universe was too hot and too young for complexity. After this bubble, the universe will be too cold and too empty for anything. We exist in the narrowest possible window of cosmic time. The universe is lonely in time as well as in space. Now I want to address a question that I am sure many of you are thinking. Can we do anything about this? Is there any technology, any physics, any conceivable mechanism that could reverse the expansion of the universe and prevent this cosmic loneliness? Let us be rigorous and scientific about this. Let us examine every theoretical possibility and see what the physics actually says. The first thing people usually think of is faster than light travel. If we could travel faster than light, we could outrun the expansion. We could reach those receding galaxies before they disappear. We could maintain contact with the wider universe even as it expands. In 1994, a physicist named Miguel Alcubierre published a paper showing that general relativity actually allows for an effective faster-than-light travel mechanism. His idea, now called the Alcubierre warp drive, involves creating a bubble of warped spacetime around a spacecraft. Space in front of the bubble contracts, while space behind it expands. The spacecraft itself, inside the bubble, is stationary relative to its local space. It is not traveling through space faster than light, but the bubble is carrying it effectively at superluminal speed. And since there is no local violation of special relativity inside the bubble, no physical laws are broken. The problem is energy. Alcubierre's original calculation showed that creating such a bubble would require something called negative energy, or more precisely, violations of certain energy conditions that normal matter satisfies. The amount of negative energy required was staggering, equivalent to the mass energy of entire stars or even entire galaxies, but with a negative sign. No known form of matter has negative energy density on macroscopic scales. However, quantum mechanics does allow for negative energy in small amounts. The Casimir effect is one example. When two uncharged metal plates are placed very close together in a vacuum, the quantum fluctuations between the plates are slightly less energetic than those outside, creating a net negative energy density between the plates. This is real, measured, and confirmed. But the amounts involved are tiny, unimaginably tiny compared to what a warp drive would need. In 2021, physicist Eric Lentz published a paper exploring warp drive solutions that did not require exotic matter with negative energy. Instead, his solutions used what he called soliton configurations of spacetime, essentially waves in the fabric of space that could carry a ship at superluminal speeds using only positive energy. However, even these solutions require stupendous amounts of energy, far beyond anything currently achievable, and many physicists have raised concerns about whether these solutions truly avoid all the problems of the original Alcubierre metric. But let us say, hypothetically, that we could build a warp drive. Would it solve the cosmic loneliness problem? Unfortunately, probably not. The fundamental issue is that the expansion of the universe is ongoing and accelerating. Even if you could reach a distant galaxy today, that galaxy is still moving away. The expansion does not stop because you visited. To maintain contact with the wider universe, you would need to constantly be traveling, constantly fighting against expansion, expending energy continuously and forever. And as the expansion rate increases, the energy required increases too. Eventually, no matter how advanced your technology, the expansion would outpace your ability to fight it. What about wormholes? These are hypothetical tunnels through space-time that could connect distant points, bypassing the intervening space entirely. Einstein and Nathan Rosen first described them in 1935 as a mathematical consequence of general relativity. But traversable wormholes, ones that you could actually travel through, require exotic matter to hold them open. Without exotic matter, a wormhole would collapse before anything could pass through it. There is a fascinating connection here to quantum mechanics. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a stunning conjecture known as ER equals EPAR. ER refers to Einstein-Rosen bridges, which is the technical name for wormholes. EPAR refers to Einstein-Podolsky-Rosen, which describes quantum entanglement. The conjecture says that every pair of entangled particles is connected by a tiny wormhole. Entanglement is a wormhole at some deep level. They are the same thing described in different mathematical languages. If this is true, it suggests a profound connection between the quantum structure of space-time and the possibility of connecting distant regions. But even if ER equals EPR is correct, the wormholes involved are not traversable. You cannot send information through them. They are not passages that could rescue us from cosmic isolation. They are more like mathematical connections in the geometry of space-time, real in some sense, but not useful for communication or travel. What about something more radical? What about directly manipulating dark energy? If we could somehow turn off the accelerating expansion, or slow it down, or reverse it, that would solve the problem at its root. The honest answer here is that we do not even understand what dark energy is, let alone know how to manipulate it. If dark energy is the cosmological constant, it is a fundamental property of space-time itself. Changing it would be like trying to change the speed of light or the charge of the electron. These are constants of nature. They are built into the fabric of reality at the deepest level. We have no theoretical framework, no equations, no mechanism by which they could be altered by any technology, no matter how advanced. If dark energy is quintessence, a dynamic field, then in principle it might be possible to interact with it. But the energy scales involved are cosmological. You would be trying to change the behavior of a field that permeates the entire observable universe. The amount of energy required would be beyond astronomical. It would be cosmic. You would need more energy than the entire observable universe contains to make a meaningful change to the expansion rate. Freeman Dyson, one of the great physicists of the 20th century, spent considerable time thinking about the very long-term future of intelligent life in the universe. He asked whether intelligence could survive indefinitely, even as the universe cooled and emptied. His original analysis, published in 1979, suggested that by thinking more and more slowly, using less and less energy, an intelligent being could sustain itself forever, even as the universe approached heat death. By hibernating for increasingly long periods and waking up briefly to think, the total subjective experience could be infinite. But Dyson's analysis assumed a decelerating universe. When the accelerating expansion was discovered, the picture changed dramatically. In an accelerating universe, there is ultimately not enough available energy to sustain even the most minimal computation. The Gibbons-Hawking radiation from the cosmic horizon is too cold, too feeble, to be useful. Eventually, the last bit of usable energy is exhausted, and no further computation of any kind is possible. Intelligence, consciousness, thought itself, becomes physically impossible. The physicist Lawrence Krauss and astronomer Glenn Starkman analyzed this problem in detail in a paper published in 1999 titled Life, the Universe, and Nothing. They concluded that in an accelerating universe, eternal computation is impossible. Any form of intelligence, no matter how cleverly designed, will eventually run out of energy and cease to function. The heat death is absolute. It cannot be fought. There is one last speculative possibility I want to mention, because it pushes the boundaries of theoretical physics in a fascinating direction. What if a sufficiently advanced civilization could create a new universe? Not modify this one, but literally spawn a new space-time. A baby universe. With its own laws of physics and its own initial conditions? This is not entirely science fiction. Certain theoretical frameworks in physics allow for it. In eternal inflation models, new universes are constantly being created as regions of space undergo inflationary expansion and branch off from the parent spacetime. If this process can happen naturally, some physicists have speculated that it might be possible to trigger it artificially. You would need to create a region of space with sufficient energy density and the right conditions to initiate inflation. The new universe would expand rapidly, forming its own space-time bubble, disconnecting from the parent universe and evolving independently. Lee Smolin proposed a related idea called cosmological natural selection, in which black holes might spawn baby universes in their interiors, universes with slightly different physical constants. If true, this could explain why the constants of nature in our universe are fine-tuned for complexity. Universes that produce many black holes, which requires stars, which requires atoms, which requires the right constants, would produce the most offspring. But even if we could create a baby universe, this would not save us from the loneliness of our own cosmos. The baby universe would disconnect from ours. It would not be accessible. It would not provide an escape route. It would be a new cosmos entirely, beyond our reach. The conclusion that physics forces upon us, reluctantly, uncomfortably, but honestly, is that the cosmic loneliness cannot be reversed by any mechanism currently known or plausibly conceivable within the framework of established physics. The expansion will continue. The acceleration will continue. The isolation will continue. And eventually, the universe will reach its final, maximally entropic state, and there it will remain. Forever. Now, before this gets too bleak, I want to step back and talk about what all of this means in a broader context. Because there is something remarkable, something almost miraculous, about our position in cosmic history. We live during a cosmological era when the universe is still connected, when light from distant galaxies still reaches us, when we can still map the cosmic web, when we can still detect the cosmic microwave background and deduce the Big Bang, when we can still measure the expansion rate and discover dark energy. We live during the brief window when the universe's history is visible, readable, accessible. Future civilizations will not have this privilege. They will have less information about the cosmos than we do. They will look out at a universe that appears simpler, smaller, and lonelier than it actually is. They will not have the evidence we have. They will not know what we know. In a very real sense, we are the lucky ones. We exist at the right time. Not too early, when the universe was too young and hot for complex life. Not too late, when the universe has faded into darkness and cold. But right now, at what you might call the cosmic sweet spot, when the universe is old enough to contain stars and planets and complex chemistry and intelligent life, but young enough to still reveal its full grandeur. There is even a formal name for this idea. It is called the coincidence problem, or the cosmic coincidence. We happen to live at the time when the matter density and the dark energy density are roughly comparable, roughly the same order of magnitude. This is strange, because for most of the universe's history, one or the other has completely dominated. In the past, matter dominated and dark energy was negligible. In the far future, dark energy will completely dominate and matter will be negligible. But right now, they are roughly balanced. And this brief moment of balance is precisely when the transition from deceleration to acceleration occurs. It is when the most interesting things happen cosmologically. And we happen to be alive during it. Is this a coincidence? The anthropic explanation says yes. Intelligent observers can only arise during the stelliferous era, when stars shine and energy flows and complexity is possible. And the stelliferous era happens to overlap with this transition period. So it is not surprising that we find ourselves here. We could not find ourselves anywhere else. But some physicists find this unsatisfying. They wonder if there is a deeper explanation, if there is some fundamental reason why dark energy has the value it does, why the transition happens when it does, why the cosmic coincidence exists. This is related to the cosmological constant problem I mentioned earlier. The fact that we cannot predict the value of dark energy from first principles suggests that something profound is missing from our understanding of quantum mechanics, gravity, or both. Let me now talk about the Hubble tension, because it is one of the most exciting puzzles in modern cosmology, and it is directly relevant to how fast the universe is getting lonelier. The Hubble constant, denoted h0, tells you the current rate of expansion of the universe. It is the number that tells you how fast galaxies are receding from us as a function of their distance. If you know h0 precisely, you know how quickly the cosmic loneliness is setting in. The problem is that different methods of measuring h0 give different answers, and the discrepancy is not small enough to be explained by measurement errors. It is a genuine, statistically significant disagreement. One method uses the cosmic microwave background. The CMB is the afterglow of the Big Bang, emitted when the universe was only 380,000 years old. By studying the detailed patterns in the CMB, you can infer the composition and geometry of the universe, and from that, you can predict what h0 should be today. The Planck satellite, which mapped the CMB with extraordinary precision, gives a value of approximately 67.4 kilometers per second per megaparsec. The other method uses the local universe. You measure the distances to nearby galaxies using standard candles, objects whose true brightness you know, things like Cepheid variable stars and Type I supernovae. Then you combine those distances with the observed recession velocities to directly measure the expansion rate. This method, led by Adam Rees and collaborators using the Hubble Space Telescope, gives a value of approximately 73 kilometers per second per megaparsec. The difference between 67 and 73 might not sound like much, but given the precision of both measurements, this discrepancy has a statistical significance of about 5 sigma. In physics, 5 sigma is the gold standard for declaring a discovery. A 5 sigma discrepancy means there is only about a 1 in 3.5 million chance that the disagreement is due to random statistical fluctuations. It is almost certainly real. So what does it mean? There are several possibilities. The first is that one or both measurements have a systematic error that has not been identified yet. This is always possible. But both teams have spent years looking for systematic errors and have been unable to find any that would explain the discrepancy. The second possibility is that new physics is required. Something about the universe that our standard cosmological model does not account for. Perhaps dark energy is not constant. Perhaps there was an early burst of dark energy in the first few 100,000 years after the Big Bang that changed the expansion history. Perhaps there are extra species of neutrinos or other light particles that we have not detected. Perhaps gravity behaves differently at cosmological scales than general relativity predicts. If the higher value of h0 is correct, if the universe really is expanding about 9% faster than the CMB-based prediction suggests, then cosmic loneliness is setting in faster than we thought. Galaxies are disappearing beyond our horizon more quickly. The timeline to total isolation is shorter. The universe is even lonelier than our standard model predicts. The James Webb Space Telescope has been brought to bear on this problem. Its superior resolution allows for more precise distance measurements to more distant galaxies, reducing reliance on the traditional distance ladder. Early results from JUEST have largely confirmed the higher local measurement, deepening the tension rather than resolving it. This is an active, ongoing area of research. We do not yet know the resolution, but whatever the answer turns out to be, it will teach us something profound about the nature of dark energy, the expansion history of the universe, and the timeline of cosmic isolation. Now I want to circle back to one of the most beautiful and haunting aspects of this entire story: the connection between quantum fluctuations and the ultimate fate of the cosmos. I told you earlier that quantum fluctuations during inflation created the seeds of all cosmic structure. Those tiny random variations in the density of the early universe grew into galaxies and galaxy clusters and the entire cosmic web. What I want to emphasize now is how remarkable it is that pure quantum randomness, the most fundamental form of unpredictability in nature, gave rise to everything we see. The Heisenberg uncertainty principle is not just a statement about measurement limitations. It is a statement about the fundamental nature of reality. A quantum field does not have a definite value at every point. It has a probability distribution of values. And when you probe small enough scales, this uncertainty becomes the dominant feature of reality. Space itself, at the Planck scale of 10 to the minus 35 meters, is thought to be a seething foam of quantum fluctuations, with geometry itself being undefined and uncertain. During inflation, these fluctuations were amplified and frozen. Quantum uncertainty became cosmic structure. Random fluctuations in a field became galaxies containing hundreds of billions of stars. The indeterminacy at the heart of quantum mechanics became the deterministic, gravitationally bound structures that make up the universe we observe. And now, the universe is expanding those structures apart. The same space-time that amplified quantum fluctuations into galaxies is now pulling those galaxies beyond each other's horizons. The cosmic structure that quantum mechanics built is being dismantled by cosmic expansion, and the dark energy that drives that expansion may itself be a quantum phenomenon, the energy of the quantum vacuum. There is a deep irony here. Quantum mechanics created the universe's richness, its complexity, its structure. And quantum mechanics, through vacuum energy, may be responsible for destroying all of that. The universe was born from quantum noise and will die into quantum silence. It emerged from fluctuations and will return to featureless uniformity. The circle closes. Let me tell you about another cutting-edge area of research that connects quantum mechanics to the expansion of the universe. It involves a concept called entanglement entropy, and it may hold clues to the fundamental nature of space-time itself. In recent years, a revolutionary idea has emerged in theoretical physics: the idea that space-time itself, the fabric of the universe, might be woven from quantum entanglement. This idea emerged from work on the antide Sitter/conformal field theory correspondence, or ADS/CFT for short, a theoretical framework developed by Juan Maldacena in 1997. In this framework, a theory of gravity in a particular type of spacetime is mathematically equivalent to a quantum theory without gravity on the boundary of that spacetime. What researchers have found is that the geometry of the gravitational spacetime is encoded in the pattern of quantum entanglement in the boundary theory. Regions of space that are close together correspond to parts of the boundary that are highly entangled. Regions that are far apart correspond to parts with less entanglement. The more entanglement there is, the more spacetime fabric exists connecting the regions. This leads to a stunning implication. If entanglement builds spacetime, then losing entanglement means losing spacetime. As the universe expands and quantum correlations between distant regions are degraded, the very fabric connecting those regions is thinning. When a galaxy crosses our event horizon and we lose all quantum correlations with it, in some deep sense, the spacetime connecting us to it has been severed. This is still speculative. We do not have a complete theory of quantum gravity. We do not fully understand how entanglement and spacetime are related in our actual universe, as opposed to the idealized models where these connections have been most clearly established. But the hints are compelling. They suggest that the cosmic loneliness we have been discussing is not just about objects being far apart. It is about the very connectivity of reality being dissolved. The universe is not just getting bigger. It is, in some fundamental quantum sense, becoming less connected, less woven together, less whole. Now I want to bring us to the question of loop quantum gravity and string theory, because these are the two leading approaches to quantum gravity, and each has something different to say about the ultimate fate of the universe. String theory suggests that our universe might be just one of an astronomically large number of possible universes, each with different physical constants and different amounts of dark energy. This is called the string landscape, and it contains perhaps 10 to the power 500 different possible vacuum states. Our universe, with its particular value of the cosmological constant, is just one of these many possibilities. If the landscape is real, then our dark energy might not be truly fundamental. It might be a consequence of which particular vacuum state our universe happens to have landed in. And in principle, our vacuum state could be unstable. It could tunnel, through quantum tunneling, to a different vacuum state with different properties. This brings us back to the vacuum decay scenario I described earlier. From the string theory perspective, vacuum decay is not just about the Higgs field. It is about the entire multidimensional geometry of spacetime shifting to a different configuration. Loop quantum gravity takes a different approach. Instead of adding extra dimensions and strings, it quantizes spacetime itself directly. It treats space as being made up of tiny, discrete chunks at the Planck scale, rather than being a smooth continuum. In loop quantum gravity, there is a minimum volume of space. You cannot subdivide space below a certain scale. Spacetime has an atomic structure. One of the most interesting predictions of loop quantum gravity relates to the very early universe. In standard Big Bang cosmology, the universe begins from a singularity, a point of infinite density where the equations break down. But in loop quantum gravity, the singularity is resolved. Quantum gravitational effects prevent the density from becoming infinite. Instead of a Big Bang, you get a big bounce. The universe contracts, reaches a maximum density, and then bounces back into expansion. If the big bounce is correct, then the universe might be cyclic. It might go through repeated cycles of expansion and contraction, bouncing each time, potentially with different properties in each cycle. In this scenario, the heat death is not truly the end. Eventually, perhaps after unimaginably long timescales, the universe might begin contracting again, heading toward another bounce and another cycle of expansion. However, I must emphasize that this is highly speculative. We do not have experimental evidence for the big bounce. We do not know if loop quantum gravity is the correct theory of quantum gravity. And even within loop quantum gravity, the predictions for the far future are uncertain. The current best evidence, from observations of the expansion rate and dark energy, suggests that the universe will continue expanding forever, approaching heat death asymptotically. There is no observational indication of any mechanism that would cause expansion to reverse. But the fact that quantum gravity might offer alternatives to eternal heat death is worth mentioning. It reminds us that our picture of the far future is based on our current understanding of physics, which is incomplete. We do not have a theory of quantum gravity. We do not fully understand dark energy. There could be physics beyond our current knowledge that would change the picture entirely. Science is humble enough to admit this. We describe what our best current theories predict, while acknowledging that those theories might be incomplete or wrong in ways we cannot yet foresee. Now, let me return to the observational frontier and tell you about some of the most important recent discoveries that are shaping our understanding of cosmic expansion and dark energy. The Dark Energy Spectroscopic Instrument, DESI, began its main survey in 2021 and released its first major results in 2024. DESI is a ground-based instrument mounted on the Mile Telescope at Kitt Peak National Observatory in Arizona. Its goal is to map the three-dimensional distribution of galaxies and quasars across a huge volume of the universe, providing the most precise measurements ever of how the expansion rate has changed over cosmic time. By measuring a feature called baryon acoustic oscillations, which are frozen in sound waves from the early universe that provide a cosmic ruler, DESI can determine the distance to objects at different cosmic epochs with remarkable precision. These distance measurements allow cosmologists to reconstruct the expansion history and determine how dark energy has been behaving over time. The 2024 DESI results were intriguing. When the team fit their data with a model allowing dark energy's equation of state to evolve over time, they found mild hints of evolution. Specifically, their data preferred a model where dark energy was slightly different in the past compared to today. The significance was not high enough to definitively claim a discovery, only about 2 to 3 sigma, but it was suggestive. If confirmed by future DESI data releases and other experiments, it would mean dark energy is not a simple cosmological constant. It would be something more complex, something that changes over time. What would this mean for cosmic loneliness? It depends on the direction of the evolution. If dark energy is weakening over time, then the acceleration of expansion might eventually slow down or even reverse, leading to a longer timeline before total isolation. If dark energy is strengthening over time, then we might be heading toward the Big Rip scenario, where the loneliness is achieved more quickly and more violently. The James Webb Space Telescope has also contributed to our understanding, though in more indirect ways. JEST has observed galaxies that formed much earlier than expected, within the first few 100 million years after the Big Bang. These early massive galaxies challenge our models of galaxy formation and suggest that structure formation in the early universe was more efficient than we thought. While this does not directly change the expansion rate or the dark energy picture, it affects our understanding of the overall cosmological model and puts additional pressure on the standard lambda CDM framework. Another important development has been the growing evidence for the existence of the cosmic neutrino background. Neutrinos are fundamental particles that interact only through the weak nuclear force and gravity. They are incredibly abundant, with about 300 neutrinos per cubic centimeter filling all of space, relics of the Big Bang just like the cosmic microwave background. But because they interact so weakly with matter, they have never been directly detected. Recent observations of the CMB and large-scale structure have provided increasingly strong indirect evidence for this neutrino background, confirming yet another prediction of the Big Bang model and helping to constrain the total energy budget of the universe. The more precisely we can determine the energy budget, the more precisely we can predict the expansion history and the timeline of cosmic loneliness. If neutrinos turn out to be slightly more massive than current measurements suggest, this would slightly increase the matter content of the universe and could subtly affect the expansion rate. Every measurement matters. Every constraint narrows the range of possible futures. Let me now talk about something called the Boltzmann brane problem, because it is one of the strangest consequences of eternal cosmic loneliness, and it connects thermodynamics, quantum mechanics, and the philosophy of physics in a deeply unsettling way. In a universe that lasts forever, in a state of near maximum entropy, random quantum fluctuations will occasionally, very rarely, produce temporary decreases in entropy. Just as a gas in a box will very rarely spontaneously concentrate itself in one corner purely by chance, the quantum vacuum will very rarely produce complex structures purely from random fluctuations. Given enough time, literally any configuration of matter can arise from a random fluctuation, including a brain. A brain complete with false memories of a past life, a sense of self, an experience of reality, floating momentarily in the void before dissolving back into the vacuum. This is a Boltzmann brane, named after the physicist Ludwig Boltzmann, who first considered similar ideas in the context of thermodynamics. The problem is this: in a universe that exists in a near equilibrium state for an infinite amount of time, these random fluctuations will produce vastly more Boltzmann branes than real observers evolved from actual physical processes. If you take any random conscious observer in such a universe and ask where they came from, the overwhelmingly likely answer is that they are a Boltzmann brane, a random fluctuation, and all their memories are false. This leads to a deep puzzle. If the universe really is headed for eternal heat death, then most conscious observations that will ever occur in this universe will be made by Boltzmann branes, not by evolved biological creatures like us. This seems absurd. It seems to suggest that we are incredibly atypical observers, which raises questions about why we should trust our observations at all. Some physicists consider the Boltzmann brane problem to be a genuine crisis for eternal heat-death cosmology. They argue that a correct theory of cosmology should not predict that most observers are disembodied branes floating in a void. This has motivated some to look for alternatives to eternal expansion, scenarios where the universe eventually ends in a definitive way, perhaps through vacuum decay, rather than persisting forever in a high-entropy state. Others argue that the Boltzmann brane problem is not actually a problem, that our ability to form reliable predictions is not threatened by the hypothetical existence of future Boltzmann branes. This debate is ongoing and touches on deep questions about the philosophy of probability, observation, and the nature of consciousness. But for our purposes, the Boltzmann brane problem illustrates just how empty and featureless the universe's future is predicted to be. It is so empty, for so long, that even incredibly improbable events like the spontaneous formation of a brane become essentially guaranteed given infinite time. That is how lonely the universe gets. The only things that happen are random quantum fluctuations, and even those are unimaginably rare. Now I want to bring us to the Fermi paradox, because the accelerating expansion of the universe adds a completely new dimension to the question of whether we are alone in the cosmos. The Fermi paradox asks, if the universe is so vast and so old, and if intelligent life is possible, then where is everyone? Why have we not seen evidence of other civilizations? There are many proposed answers to this question, but the accelerating expansion provides a particularly haunting one. Consider this. Even if intelligent civilizations are relatively common in the universe, even if millions of planets across billions of galaxies host technological species, the accelerating expansion means that most of these civilizations are completely, permanently, irrevocably cut off from each other. They exist beyond each other's event horizons. No signal can pass between them. No communication is possible. No evidence of each other's existence can ever be exchanged. And it gets worse. Even for civilizations that are currently within each other's event horizons, the window of time during which communication is possible is finite. Two civilizations separated by, say, 10 billion light years might currently be able to exchange signals if they started now. But the accelerating expansion means that this window is closing. At some point in the future, the expansion will carry them beyond each other's horizons, and communication will become impossible forever. This means that civilizations have a limited window to find each other, a limited window to establish contact, a limited window to form a galactic community. And that window is narrowing with every passing second. The universe is not just lonely in the sense that everything is far apart. It is lonely in the sense that the opportunity for connection is actively diminishing. Time is running out, and has been running out since the moment the universe transitioned from deceleration to acceleration 5 billion years ago. This adds a poignant urgency to the search for extraterrestrial intelligence. If other civilizations exist, the best time to find them is now. Not tomorrow. Not next century. Not next millennium. Now, because every moment that passes, the universe gets a little bit lonelier, and the chance of ever making contact gets a little bit smaller. Let me now address the concept of cosmic horizons one more time, because I want to make sure you understand a subtle but crucial point about the nature of our isolation. There is a common misconception that the edge of the observable universe is a fixed, permanent boundary, that the observable universe is like a room with walls, and we just cannot see past the walls. This is not quite right. The edge of the observable universe is not a physical boundary. It is a limitation imposed by the finite speed of light and the finite age of the universe. Light from regions beyond this edge simply has not had enough time to reach us yet. In a non-accelerating universe, the observable universe would keep growing forever. As time passes, light from ever more distant regions would finally reach us, and our observable universe would expand without limit. Given enough time, we would eventually be able to see everything. But in an accelerating universe, this is not what happens. The acceleration puts a permanent cap on how much we can ever see. There is a finite, maximum region of space from which we can ever receive information, no matter how long we wait. This is the cosmic event horizon I discussed earlier. And unlike the particle horizon, which grows with time, the event horizon is fixed in a sense. In terms of what will ever be accessible to us, the boundary is set. No new regions will ever become accessible, and existing regions are constantly being lost. This is what makes accelerating expansion so qualitatively different from decelerating expansion. In a decelerating universe, the situation always gets better. You always see more with time. In an accelerating universe, the situation always gets worse. You always lose more with time. The universe's accessible content is monotonically decreasing. The universe is, in a very precise mathematical sense, getting lonelier every second. Let me quantify this one more time so the scale really hits you. The current event horizon is about 16.7 billion light-years in moving distance. The total observable universe extends to 46.5 billion light-years. That means roughly 64% of the currently observable universe is already beyond our event horizon. We can see it because its light was emitted long ago, before the expansion carried it beyond our reach. But we will never receive any new light from it. We are watching its history play out in delayed replay, but we have already lost contact with its present and future. And as time progresses, more and more of the universe crosses that horizon. Eventually, Only the gravitationally bound local group remains within our causal reach. Everything else is gone. Lost, unreachable, unobservable, unknown. I want to take a moment now to talk about the concept of information in this context. Because the loss of cosmic connectivity is not just a loss of physical access. It is a loss of information. In physics, information is a fundamental quantity. It relates to entropy, which is the measure of disorder or the number of possible states a system can be in. The second law of thermodynamics says entropy increases over time. But there is another principle, often considered equally fundamental, that says information is never truly destroyed. In classical physics, if you know the exact state of a system at any moment, you can in principle calculate its state at any other moment, past or future. Information is preserved.